Thanks, Sai. So anyway, we do have some number of hardy souls who have survived the festivities yesterday. So, so we will start slowly. I guess being an organizer of this conference, I suppose the plan was to listen to what the other speakers had to say, including Carl and Sai and Saikat and others, and try not to be have too much of an overlap, but sufficient overlap that you get the idea. Because after all, the whole workshop is on precision measurements and quantum metrology. So half the people are going to talk about quantum metrology at least. And there is a limited amount that you can talk to you about. So, so I thought after various permutations and combinations, I thought that I'll talk about some work that we did a while back, okay, which is connected to this. And it was, of course, done with all these very nice people, including Carl, who was here, Animation, Sergio, and Shalini was my first PhD student. So, right. So what are we going to talk about? To talk about slight variation in the kind of discussion that we have had related to quantum limited metrology, adding a slight twist to it. And reason I'm talking about it is that, first of all, it sort of underlines something I think Carl had said in his talk to you, but I will actually put it up as a slide because I think it's worth writing it down. I will get to that in a second. And it also tells you how to think a little bit beyond and see where it goes, starting from what you have learned. And finally, it also encompasses an attempt to sort of make a connection with the possible experiment. So the idea is that you'll try to do a calculation which may get an experiment group interested. Of course, this was done more than 10 years ago and nobody quite got interested, but that's okay. You learn a bit from it. And maybe sometime in the future, somebody may pay attention to what was done. So to communicate to you all these stages, I thought I will sort of rehash this work that was done back in 2008 or so, and 2008 to 2012, and talk to you about it. Because these are things that you all quite know, that you have to do some quantitative measurements to understand the physical world in a quantitative manner. And the fun part, of which there are many levels, is that the measurements itself sort of find a description within those theories. And there are discussions about how to understand measurements within quantum mechanics. That's ongoing, but that's not really the topic of this talk. Really, so it always brings to my mind this picture by Escher, where you kind of the two hands drawing themselves, or very many other prints by Escher, which allows sort of one thing to happen, which makes the other thing happen, and it comes back to itself, which is always an interesting idea. So the limited question, as I said, not exactly what is measurement in detail. That's a subject of a different talk. And what do we know about it? But it's more about it's a limited question that we have been asking. What are the fundamental and practical limits on precision in measurements within the framework of a theory like quantum mechanics, right? So you have to always talk within that framework. And one of the questions that has been asked explicitly and not explicitly, what are the resources required to achieve that precision? And how can we achieve those limits? So these are questions that we have discussed already before. Both three speakers have at least talked about it before. So let me just simplify that discussion with some cartoons. So what are we trying to do? Of course, we are talking here in the context of single parameter estimation. And we have discussed this. Various speakers have called the parameter various names. So I call a totally different name. So we have seen it as lambda, phi, psi, theta, whatnot. So let's call it phi for the time being, and it's some parameter associated with some essentially classical system that you want to measure. And what you're employing to do it is, in very oversimplified terms, some n particles, which together we constitute let's call it the quantum probe. And as we have seen before, one assumes that essentially the value of the parameter phi is sort of imprinted on these n particles through this Hamiltonian interaction Hamiltonian that connects that sort of has an effect on these particles, which is dependent on this phi. So what do? You kind of send these guys through, something happens to them, and then what? Right? Then what the question is, what you do? You kind of do sort of simple readouts on it. So we ask it, okay, what state are you in? But in a relatively gentle manner, because in a sense, there is a little bit of a logical issue here, in the sense that, okay, you use these guys to measure phi, and then you say that I'm going to measure those guys. So who's doing that measurement? Right. So that's a part of the theory that we are really not going to talk about. I would say that in anticipation, since I've heard it before, Carl in his talk next week will be talking about some of these aspects, like what happens when you do that. But let's just slide it under the carpet and say that for these probe particles, you are going to ask very simple questions. Are you in this state or not? Or are you here or there? Just very simple questions. So that, but from that, you are going to actually try to compute or to estimate the value of this parameter, which is a real number with some very large number of decimal places, which is what you are trying to do. You're trying to do precision measurements, and you're trying to use quantum resources to do it better. So, and because you know that in quantum mechanics, you can do much more funny things, like I can make a cat out of it, a Schrodinger cat kind of state, and send the cat through, and then cat becomes something else, right? And you can do a slightly different kind of cat, and then you can ask the question, okay, what has happened? And from that, can I figure out what the value of phi? These are things that you have already seen well. So one thing I would like to again underline here is that we're asking what's the best possible estimate of the parameter that can be obtained using the available resources. So that's also important. You cannot assume that you have got infinite resources at hand, because then pretty much anything is possible. So you have to consider the fact that you have to be using a limited resources. So how do we quantify those resources? The quantification is in this simple picture, let's call the number of particles that make up the probe as your resource. Now, in general, n is simply a placeholder for the real resource in that particular metrology scheme. And it is useful to have this simplified picture where n is a number of particles that you're using. It could be we have talked about the circulating power in the interferometer as a resource, and yesterday we heard all the different ways in which increasing the circulating power in the LIGO interferometer can create problems, like small pieces of the mirror exploding and all that stuff, rather terrible things. So there are constraints on what you can do. And so without constraints, okay, everything is possible. So you have to worry about that. So that's sort of the question that is asked. So the way I think about it, which I thought I would also share with you, may be different from what you have heard from others also. But so let's analyze this question. How do you get at this? What do I want to find? I want to find a connection between n and the uncertainty delta phi with which I can make this estimate measurement using the resources. So that's sort of what we are after. So how do we think about it? So first question is, to what extent does that depend on phi itself? Well, we have seen this question yesterday in Saikat's talk, where he said that in some cases, the value of phi also, the value of the measured parameter also comes into play. And you have to choose a point where things are optimal to operate on. But that is just that is part of the design of the experiment. But in general, the idea is that the uncertainty really is a property of the measuring device. So how do we see that? We know that very well. So this slide was made back in the day when something else was popular. So I got this ring up there, right? Which is, if you remember, is from the Lord of the Rings movie. And of course, it's a very strange ring which kind of doesn't bounce and all that, you know, that if you see the movie. But or notwithstanding, you want to try to figure out what's the weight of that, how much gold goes into it, or whatever other material that is supposed to go into it. But that's a different question. But the thing is that you know that, okay, if you try to put it on a balance like this, that's probably not going to yield great results, because that thing is hardly going to respond to the ring that you placed, despite it being a magical ring. You may have a better luck if you go to the market and try putting it on that, but that's probably still insufficient. And so you eventually have to go to somebody who has something like this in a jewelry shop and get a weight of that. So you can see that the uncertainty associated with the measurement of the weight of the ring is tied to the object that the device you are using to measure. So that's a very obvious statement. So let's kind of get rid of that ring, or some people did that in the movie, so let's not worry about it. So in our particular case, what I was trying to get at is the point that when you're talking about quantum metrology, the measuring device is the quantum state of the probe. So it's that thing inside Hilbert space, which is moving around, and you have means of getting out what happened to the quantum state when you subject it to some process or some kind of violence that depends on the parameter phi, right? So but the action is happening inside Hilbert space, which also kind of tells you that this is probably a good idea, because one of the things you are kind of taught when you are teaching, when you are first learning quantum mechanics, is that these correspond to very, very what you call fragile systems, which kind of take off if you even try to look at it carefully, right? So these guys' states are liable to change very rapidly if you actually subject it to some kind of influence. So therefore, it seems a priori like a very good idea to try and use a quantum state to do your measurement. So that sort of that motivates why you would want to think about quantum limited metrology. But this I do not want to repeat again. So we have seen, so how well can you do the measurement? So sorry, our phi became a gamma here because of inconsistencies that happen when you mix various talks together. But apologies for that, but gamma, phi, psi, etc., theta we have used. So I'm sure you're familiar with it. But the idea is that the measurement uncertainty is sort of greater than the rate at which the quantum state, which is this ds, this little line element in the space of density operators, change with respect to gamma. And we've seen that, okay, this can be bounded essentially by the quantum Kramer-Rao bound, which whose simplest form Carl had talked to you about yesterday, which is in terms of the operator semi-norm of the generator that generates change in gamma on the quantum system that you are using as the probe. And the semi-norm is defined as the difference of the largest and smallest eigenvalues. And you already heard that how that reduces the problem essentially to a qubit problem, in the sense that you would want to create superpositions of eigenstates corresponding to these two Hamiltonian, these two eigenvalues, sorry, and then let it evolve under this Hamiltonian that is coupling to the that has the parameter in it, and then that will give you sort of the most bang for your buck, that it will let you do that to make as precise a possible measurement. So this I am sort of okay. Let's maybe right. So this is of course a fairly famous experiment which sort of contributed to the or trouble was central to the Nobel Prize given to Tharosh. It's from that group. But this is their scheme for using a quantum system to measure something. In this particular case, what they're trying to measure is the number of photons in the electromagnetic field that is sitting inside this cavity. And this is the typical Ramsey interferometry scheme you described in the context of a particular experiment. So you know the objective that they're trying to do, which is to figure out how many photons are there in this little field, which is denoted by this blue. So I took this example because it kind of corresponds very well with the cartoon that I had done very earlier, and even the field is pictured as blue here. So well, maybe not dark blue that I use, but light blue, but whatever it is. So, but the thing is that what is happening? What happens is that you start with atoms in a Rydberg state out of an oven, and then you kind of put it in a superposition. Okay, and then you put of two different states, some n equal to 52 and 53. Some these are Rydberg atoms which are in very high principal quantum number states. And then you put a superposition, put it in a superposition, and what it does is that, and then it moves and goes through this cavity, and it interacts, as I said, dispersively with the field, in the sense that it doesn't quite absorb photons or emit photons into that field, because that's what you're trying to measure. That would be kind of bad if you change that. But it weakly interacts with that field, and these superposition, the two components of the superposition pick up a relative phase, which depends on what's the strength of the quantum field. And it comes out, and you do another little thing to it, which these two things together form what's called the Ramsey pulses. And it comes out, and you kind of measure the state of the atom, and you can get an estimate of what is happening. So in terms of qubit states, in terms of states represented in a block vector, what's happening here is that you are starting with a system with two basis states. So it's a two-dimensional Hilbert space effectively, n equal to 52 and 53 being whatever the labels to the states if you want. And you start it in a particular state, then you put it with a pulse of a laser pulse or electromagnetic wave, or microwave pulse, you kind of throw that to a state that is on the equatorial plane. So you've created a superposition of your 0 and 1. And then when it passes through here, this guy recesses because of the influence of this field, and it picks up a certain phase phi, which is dependent on the strength of the field. Right? So this phase information, as we have discussed before, it's kind of is transformed back into information contained in the population of atoms by the second pulse, which sort of rotates it about notice that the first rotation is about the y-axis, it does that again. So this angle that it picks up is now is essentially the same as this angle. But now the idea here is that now the projection of this vector onto this z-axis is going to give you the probabilities for the atom to be in state 0 or 1. So just by counting how many atoms come out in each of these states, you can get an estimate of this angle, which in turn is connected to your strength of the field. So in these steps, you are getting an estimate of So one of the points here is that the way these atoms couple to this field is given in this form, where each of these guys are coupling independently to the quantum field, which is significant for this particular discussion. So, and in particular, you can write it in this form. So this is what I've kind of shown here, because all that is happening is a rotation about the z-axis as a result of the interaction between whatever is you're trying to measure and the quantum probe that you have sent through. Right. So as Carl was mentioning the other day, the language of quantum circuits gives an excellent view, picture of how to understand and think about this process. So let's run through this. So what I'm claiming is that whatever we saw before, and I'm sure you probably already have seen this, is basically given by this quantum circuit. So what's happening here? That's kind of easy to see. What's happening here is that, okay, at this point, I'm representing all the atoms in this state. Then what do? I do Hadamard transformations, which take 0 to 0 plus 1 and 1 to 0 minus 1. So what I have done, effectively, your 0 becomes 0 plus 1 by root 2. So the Hadamard gates represent this action, that little pulse that was on the left side. Then you have got the parameter dependent evolution, which acts independently on all these qubits, right? Each of them is subject to this evolution. And one can represent it by the fact that this vector turns around a little bit, but in the circuit picture, this is what it talks. This is how you would represent it. On each of these qubits, you have applied a small unitary that depends on the parameter phi, and it's given by a z rotation. Then the last step is, right, you do this again. We had a much, which if the state was in the 0 plus 1 by root 2 state, it would have come exactly back to where it started, because 2 times Hadamard gate is the identity. Therefore, if this thing had not happened, the state would have come back to where it started. But this thing did happen. Therefore, information about this phi is there in the final state. And then you do a bunch of measurements in the Z basis, ask how many atoms are in state 0 or 1, and you will get essentially what you can compute out of these clicks is the expectation value of this operator, which in this state that you receive out here, which is a superposition of 0 and 1, we can calculate, it looks something like this. And from that, you can do a computation of the uncertainty in phi, which is just a straightforward propagation of error. And you will find that the answer is the scaling of these uncertainties goes as 1 by square root of n. Right. So, which is a short noise limit and so on that you have seen quite a bit before. But of course, if I take my original Hamiltonian and find the semi-norm, it is easy to show that the limit or the bound given by the Kramer-Rao bound is that delta phi should go as 1 over. But in this case, we have gotten only 1 by square root of. Okay. So, right. So what has gone? What's the issue here? Why didn't we not get to the bound? Because obviously there are many things that you are probably not doing the most ideal thing. So this is a choice. It looks like a very simple choice to estimate phi. It works, but what it does is that the measurement uncertainty is scaling is 1 by square root of n. When you know that the Kramer-Rao bound tells you that if you try hard enough, you can do this. And there are, of course, a couple of questions there. One is that, is this the best state for your quantum probe? As I showed in that picture in the beginning, that little cartoon in the beginning, you can do more fancy things with these n atoms. You can bring them together, put them in a cat state, and then do the cat into another cat transformation. Maybe that will give you something better. And also there is a question of, okay, is this the best measurement you can do or readout you can do in the other end? And this again was discussed in the previous talks. The derivation of the Kramer-Rao bound sort of, as Carl puts it, sort of whispers to you what is the measurement you should do. Right? So, so how can we do better? Well, obviously the answer is yes. Otherwise, all this workshop probably half of it won't exist. It will be just precision measurements, right? And not the remaining part. So, right. So this also is something that we have that has been discussed here before. But so what do we do? So, well, let's try the cat part. So how do you create the cat part? You start with everything again in the same state. You do a Hadamard on one of them, which puts that one in a superposition of up and down. Rest of it is here. Then you can do a sequence of controlled NOT gates, which will flip the second qubit dependent on the state of the first one. If the first one is down, it will flip the next one. So what it does is that the state of these two qubits then become something that looks like this, because we started with the first qubit in up plus down by ρ2 and the second one in up, right? But this C0, what it does is that when it finds the first one in down, it flips the state of the second one to create this state, which is an entangled state, right? So you can keep on doing this step by step, and then in the end, you will get a what's called a cat state or a macroscopic, or a what one would kind of say that it's a superposition that approaches something macroscopic, because you got this state in humongous state in which all the atoms are either in the spin up, either in one state, or all of them are in another state superposed. Okay. So that's why you kind of call it a macroscopic state, because you got a whole bunch of things that is in one state, and then you're going to superpose it with a whole bunch of the same bunch of things in another state, right? So right. So then the same dynamics happens. Each of them are individually influenced by the field in that cavity by the same unitary, which is a z rotation of each of them. And you'll find that each of these pieces pick up faces that look like this. That's fairly straightforward to do. And you can sort of maybe pull out an overall face and then say there is a relative phase that now goes as n times phi. Okay. Earlier, for each of these individual atoms, the relative phase went as phi. Each of the components of the superposition of each atom state, and it was a product state. It was not entangled. Each of them went as phi. Now the phase is going as n phi, and that after you do this sequence of operations, which is sort of one that uncats the cat state, okay, it kind of separates all these other guys out, but in the process, the relative phase that has been picked up, okay, kind of skipped the previous step there, doesn't matter. The relative phase that has been kicked up, all of it is given to the first qubit. Okay. This is a what's called phase kickback, which is a very fun thing that you can do in quantum mechanics, cannot be done really in classical mechanics. So all the burden of phase that was relative phase that was shared between all of them is sort of quietly moved to one of them. But it's not an essential step, but I just want to show it there. And then, as we had heard before also, measurement of this guy will essentially, if you do the same calculation, you will find that the measurement uncertainty will scale as 1 by n. And in a sense, the relative phase or the fringe, the pattern formed by that first qubit is now going n times faster, because the phase pickup is n times phi. It is not just phi. So therefore, if phi changes from say 1 to 1.1, the entire thing changes a lot, because the phase pickup is n times phi. Therefore, you're much more sensitive to phi than the case where the phase was just proportional to phi. Okay. So that's sort of key to this idea. And of course, creating cat states is hard, and then you can always ask the question: is this the best one can do? Can you do better? Okay. So that's not a question that has been addressed before in here. So that's sort of what I really want to address, right? Can you do better, and how do you think about that? Okay, and what all trade-offs you have there, and so on. Right? So the next step, therefore, to think about can you do better is to now abstract away from these pictures. And again, the language of circuits sort of gives you a good way of doing that. Right? So we have been talking about specific experiments that somebody did. So let's now take a step back and evaluate and see where you can change things around. So what do we have here? We have here a preparation of the state of the quantum probe. Okay, taking those all n things and putting it into this cat state or any other dog state or whatever state that you like. That's a preparation scenario. And then there is dynamics part, wherein the parameter is imprinted upon your quantum state by the interaction of the probe, quantum probe, with the whatever that you are measuring. And so far, in both examples that we have considered, our dynamics has this form where the parameter imprinting is actually happening independently on each of these units, probe units, which for our picture are conveniently qubits. And finally, reason why I kind of showed the phase kickback scheme earlier is to impress upon you that there is a little bit of thought you can put into the readout process also, wherein which may help you extract the information you are looking for in a better way. So therefore, we see that there are these three kind of compartments that you can think of. Okay. So this is what he said last time. So I put it up there because it's worth writing down, right? Because once you have this sort of picture, right, it allows you. Where did my picture go? It allows you to now see where you can sneak by and violate the ingredients. So if you know the ingredients that go into, say, the quantum Kramer-Rao bound in this scenario, right? You can now think of what ingredient you can change so that you can go beyond this 1 over n that we have been talking about. Okay? So that's the purpose of putting it there. So right. So how do we do that? We do that. So we make, okay, this guy we have dealt with sufficiently. So the preparation part, we make it into a box. That's the preparation stage. The readout, you make it even more complicated. Let's bring in ancillas and other helpful agents to get a better readout if you want, right? And you can show that twiddling around with these guys is probably not going to buy you much more. Okay, but you see that it motivates the question, okay, why not I change stuff out here? Because the dynamics was a bunch of little boxes. So why do I want to be confined in those little boxes? Why don't I expand my box and say that I'm going to do a dynamics that is sort of not really compartmentalized in the same. Okay. So where it leads to, so one gigantic unitary that imprints the phi into on the quantum probes. So then we can now start considering Hamiltonians that may contain coupled terms between the individual probe units. So earlier, this was a sum over just HJs. There was no HJHK or HJHKHL or any such term. Okay. So if I take only the kth power, basically these are the terms that I'm considering. The old Hamiltonian that's there, but raised to the power k. The question is, raising to the power of k, does it give you some kind of superpowers in some sense, right? Good, because, and obviously, well, you can kind of do earlier when we talked about the operator semi-norm and the quantum Kramer-Rao bound, it doesn't really tell that you have to use one kind of Hamiltonian. So you can apply the same rule here. You can try to compute the operator semi-norm for a Hamiltonian that looks like. And you see that this goes something like that. So upfront you have got a sort of n to the power k term here. Here notice that lambda and small lambda are the largest and smallest eigenvalues of the small hj, not of the combined thing. So, and therefore your measurement uncertainty can therefore in principle scale as n to the 1 over n to the power k. Not just 1 over root n, not just 1 over n, but why not 1 over n square, 1 over n cubed or whatnot. Of course, you all know the problem here. How do we engineer Hamiltonians that look like this, which is also dependent on your parameter. Notice that this is the non-parameter dependent part of it. The parameter itself is sitting somewhere there. So that's where your kind of challenge lies. So this was something that was pointed out in this paper, these two papers in two different ways. Right. We can ask some other questions, which is to say that, okay, I don't want to be bothered to making a quantum cat state, a cat state and all that. Suppose that's really hard. Suppose I just throw individual qubits at it, but have this Hamiltonian. Do I get something better? And I probably don't want to do a complicated readout also. I want to keep the readout simple because, right? So the parameter dependent evolution Hamiltonian is often sort of given to you by the system. You're not manufacturing it, right? Therefore, in the presence of such a Hamiltonian, which has these h sum over hj power k kind of form, can I do something simple and still get something that is better than the conventional, idea of 1 over root n and 1 over n scaling with respect to my resources, which is the number of quantum probes. And it turns out that even with a separable input state and a separable measurement, one shows that the bound is essentially scaling as 1 over n raised to k minus a half. Okay. So the so when k equal to 1, this of course reduces to 1 by root, and this all we know. When k equal to 1 is the case we have discussed before. So with a complicated preparation and readout, you will get 1 over n, otherwise you get 1 over root n. But here what we found is that if you let go of the complicated preparation and readout, you still get, for k greater than 1, you still get an advantage. Or what you lose by giving up all those boxes at the beginning and the end is just a factor of half in the exponent. So, right. So we can do better than 1 over n even with k equal to 2 and no fancy preparations involved, as per this bound, which is quite based on solid basis, right? So, so in our earlier picture, right, in the example that we have considered, the Hamiltonian we had was sum over the spin the sigma z operators of the individual. So that thing inside the bracket is essentially the what we call big Jz, the total spin component, if you want, along the z direction, right? Because these are individual spin components along the z direction, if you think in terms of spin. Okay. So what we are really talking about is Jz to the power k as your Hamiltonian, or in equivalently, you can even have n times Jz. You'll see that this also can happen. Right. So this all looks very fine. The question is, okay, how will it work? So, so any questions or comments? Yeah.
Yes. So if we introduce the nonlinearity, let's say to square, what we are doing is we are introducing probe interaction, right?
Yes.
But in the earlier case, in the preparation, we were using probe interaction when we are using that C0 gates.
Yes.
So why using interaction in the preparation is not giving us the advantage, but in the dynamics giving us the advantage?
Well, I guess the short answer to that is that the putting the square here is what actually connects to the quantity you are measuring. Like all the stuff you do here and here has nothing to do with what you're trying to measure.
I see.
So there is a limit to what it can do, right? What it if you do stuff before and after. But here you are kind of directly meddling with the thing that imprints the phi on your quantum probe. A different way of thinking that people are saying is that, okay, if you expended a certain amount of energy or action in imprinting the value of phi onto your probe, you're actually cheating here because you have now introduced, wherein you had n terms before, now you have got n square terms. Right? Each of them has a factor of phi. So are you really sort of within quotes cheating here, right? You're kind of hiding the fact that you are expending more resources in the sense of the thing that imprints a phi dependent phase on the quantum probe is doing more, because if you expand this whole thing, the whole square, you've got now n square terms.
Yes.
Earlier you had one n. So that's all true, right? So so if you do a what you call a real honest count of resources, you have to bring that in, right? And you will find that in some in a very specific sense, you are not actually doing within quotes any better than the previous case. Okay, in terms of if you account for all the resources that are there. Maybe Saha will mention that it's something that he has been working on. But the question is, do you want to do that? Because ultimately, what are you trying to do? You're trying to get an estimate of phi. Okay, and it's given to you kind of for free because it is in the whatever quantity or whatever system is imprinting your phi on your quantum probe is doing it for you. You are not really working for it. Okay, so in that sense, does it have to be counted as a proper resource when it comes to the quantum metrology? Because bringing in all these qubits, all these particles, putting them in a state that you want, reading them out are stuff that you have to do, right? So you have to work on it. Therefore, are this do I want to consider those as the real resources? And in this case, let's take that view. Although in a different sense, you can do an honest resource counting, and you will show that this is not particular, is exactly equivalent in that sense to the linear case. Good question.
Thanks.
Right. So, okay. So let's go ahead. So let's take an example with k equal to 2. So we have dispensed with making the cat state and all that. So we can talk in terms of each of the probe particles independently. And they are subject to a Hamiltonian, that is, now let's take it as gamma jz squared. Okay. So let's initialize the probe in a what's called a spin coherent state, which is essentially this JJ state rotated. Okay, so JJ state is basically all of them pointing up, all the Z components also pointing up, and then you rotate it a little bit, so you'll get a what's called a spin coherent state that has an expression that looks like this, right? And you subject it to evolution under this Hamiltonian. So this is an n qubit state because capital J is the total spin of all n qubits. So all of them is in a spin coherent state, right? Of which the simplest one is the one without, where the beta is 0. That's just a JJ state, which you are all familiar with. Okay. And you subject it to JZ square evolution. The JJ state wouldn't do anything, so that's why you want to go there. And you can compute what happens. Well, I am not going through that computation. And then you say, okay, this is the measurement I am going to do on the quantum probe. And these are independent measurements on each of the qubits, not any joint measurement. So there is no big box on the end either. And you can go through this calculation and compute the measurement uncertainty that you get. So the significant point here is that you do get a scaling that goes as n raised to 3/2 without any initial entanglement or without any fancy phase kickbacks at the end of the measurement. Just simple input, relatively simple input, what you may call classical like if you want, and simple readouts, but a nonlinear evolution. So you can compute that the delta phi indeed can go like this. But the thing is that, and the optimal value of beta is so and so. You can now try to plot delta phi as a function of phi itself. Okay, with some scaling and all that, but it doesn't matter. It's a function of phi, and you find that it's a very complicated function that looks like. Okay. So what's happening? What's happening here? What it's saying is that your delta phi becomes small only for a particular value of phi, and that value is very small. In other cases, you're doing pretty bad, and you've got all this crazy behavior for your uncertainty as a function of phi. Therefore, there is one operating point that you have to go to at 0, where this will work. Everywhere else, it is pretty fragile. Why is that? The reason for that comes from the fact that you are using the JZ square Hamiltonian. So if I visualize the spin coherent state by its Q function on a sphere, so it's sort of a state of many spins pointing in this particular direction with a certain spread around it. And I calculate what happens to it under the JZ square Hamiltonian. Sorry, this is not the one. You find that it kind of gets all messed up, okay, all over the place. And that's the reason why it really works only for short times and at a very specific point. Because that asks the question, what if we had something like this, where the Hamiltonian is such that your spin coherent state just goes around very nicely. So the answer to that is that the interaction had the form n times Jz rather than Jz square, then obviously you're going to get something like this, but without the associated problems that I tried to explain to you earlier, with the it being very sensitive to what value of phi you are working at and things getting very bad very fast. So turns out both these couplings as effective couplings can exist in real physical systems. Okay, both these kind of interactions with the probe. And the NJZ is virtually indistinguishable from JZ square in terms of the scaling. Okay. And one way of saying that, okay, saying that are you cheating here? Are we replacing each of the qubits with things that have frequency that's n times the ones that you originally had? Because NJZ looks like that, replacing JZ with n times. The answer to that is that this is a little bit unacceptable, because then the nature of the qubits that make up the probe has to change with that, because for a different n, you need to get a different kind of object. So you don't want that. You want genuine NJZ effective coupling appearing out of the natural connections or couplings that are there between the probe units that you are using. So we had this picture of a nonlinear Ramsey interferometer, in which it's sort of a double interferometer, in which after it does the first round, okay, with possible nonlinear interactions, these two beams can sort of interact with themselves mediated by some nonlinear medium, some matter, because light doesn't directly interact with light. So, and then it can do an NJZ type of interactions, which can actually, if you compute it through, can lead to the kind of advantages that can possibly be there. That kind of advantages we discussed before, where the scaling goes as 1 by n raised to 3 by 2. So that was just a aside. So in the last 10 or 15 minutes, I just want to talk about sort of our attempts to find a system where these kind of Hamiltonians may be there, and to try and sort of compute whether an experiment that will measure something useful can be there. The whole point of this is probably not to explain to you that this experiment is great and you should try it, but just to impress upon you that it is, while, okay, finding the bounds and going beyond it and talking about nonlinear interferometry is all nice, it also helps to think through and try and connect it to a possible realistic scenario. Okay, because it also teaches you a whole lot of other things, right? So what we considered a place where you can have the kind of nonlinear Hamiltonians that we talked about is a Bose-Einstein condensate. At 0 temperature, the Hamiltonian is sort of is given by this one. Okay, you already see that there is a term with pair of size and side daggers sitting there. This is in the and if you assume that all the atoms have the same spatial wave function, then one can simplify this whole expression by writing this field operator as essentially wave function times an A dagger. So all it says is that action of your creation operator A dagger is to create a particle. What is its spatial wave function? Its spatial wave function is psi naught, because all of them have the same spatial wave function is an assumption that we have put in, which is going to kind of come and bite us a bit later, but let's put that in. Okay. And then you can write down the same Hamiltonian now in terms of creation and annihilation operators like this. Right. So we are considering a two-mode BEC in which all atoms can in the BEC can occupy two internal states. Their spatial wave functions are all identical for the time being. You put one in, but it can have two different internal states. And the way one thought about it is to say that, okay, all these atoms are put in one of those internal states and they're all cooled down to form the BEC. And then you drive the atoms with some kind of field, required pulse, to obtain the required superposition of internal states to start with. And then we look at the dynamics after you have done that. So you put it in a superposition. We are assuming that the two internal states see the same trapping potential, so that their spatial wave functions are the same, because if they see different traps, they are going to go and settle in two different spatial wave functions. But again, that's not exactly a justified assumption in a realistic scenario, but we do it all the same. And we also assume that the processes that are happening are elastic in nature. Okay, in the sense that two atoms in the internal state 1 will go to two atoms in internal state 1, similarly this and this, but two atoms in this state doesn't end up in that. Okay, because that involves a change in internal energy of each of the atoms, and you don't want it getting it or losing it somewhere. So these are the assumptions that we make. Again, going back to that slide, let's just be clear about the assumption, so that if you want to do better, you know where to start looking. Okay. So with these assumptions, we can simplify our earlier Hamiltonian, although it doesn't look very simple. It simplifies to this. Essentially, we are saying that if you look at these terms, some of those guys have been now avoided, the non-elastic collision terms. So this is, it destroys two atoms in state 1 and creates two in state 1 again. So that's a 1-1 going to 1-1 process. Similarly, 1-2 going to 1-2. The other guys have been now taken out of the Hamiltonian. So, well, that's just what I said. These are describing those processes with appropriate coupling constants, G11, G22, and which you call G12. So, right. So now what? Now to come back to our earlier language, it is convenient to define these two new operators. This simply counts the total number of atoms in the BEC, because it counts the number of atoms in state 1 and the number of atoms in state 2. After all, we only had atoms in states 1 and 2, no other state. So this just counts the total. And define the JZ operator as essentially the difference between the number in 1 and number in 2. Right? So that's again like the total spin Z component. You're just counting the number of guys which spin up and subtracting from it the total number of guys which spin down. So that will give you the net spin in the Z direction. So that's essentially what you're doing. You're just relabeling spin up, spin down with states 1 and 2, which are internal states of the atoms. So if you mess with it, you can rewrite the Hamiltonian in this form. Okay. And lo and behold, in this expression, we have the kind of things that we need, we are looking for. We have got a term that is m times jz. We got a term that is jz square with some constants in front. And what are those constants? Those constants turned out to be some combination of these scattering constants G11, G22, and so on. So these constants that are appearing here are not terribly interesting because these are essentially static properties of your atoms that you are using. So they're not actually exciting things to measure. Okay, but then one can think through further, and you will find that some of these scattering lengths can have dependence on external parameters like magnetic fields or things like that. So in that context only, it becomes interesting. So right. So I have separated it out into these two pieces in the sense that this whole thing does not have any Jz or Jz square. Therefore, it kind of acts identically on atoms in state 1 and 2, and therefore it produces no relative phase between your states 1 and 2. So they are in a sense uninteresting to you because they are overall phases which you can kind of not bother about. The other one does relate to a relative phase between 1 and 2. Right? So what happens? So you can now write down the Hamiltonian as this part that doesn't depend on, that does not produce any relative phase, and this part that does produce a relative phase with a little bit of a change in which I have just taken n-1 operator and just called it n. Okay? Because it's a large number of atoms. And again, remember, these are the two things that are appearing in front of your what do you call parameters that are appearing in front of these two terms. And in addition, there is this additional term which again comes from actually doing the spatial integration, assuming that all atoms are in the same state. So this is some number. So it's a wave function to the power 4 integrated over all of space. And so then, right, you can compute. So in the ideal case, so what is happening? So you got all atoms with a certain wave function, which I pick color blue, right, sitting with this wave function. And as a result of the relative phase picked up, you'll find that now you got two different things. One corresponds to state 1 and the other corresponds to state 2, and it kind of picks up some kind of relative phase. We further looked at realistic atoms and looked at rubidium 87 and realized that one of our constants gamma 2, and for that case, for rubidium 87 with these two levels as the states of interest, have their corresponding scattering lengths arranged in this nice way such that this quantity gamma 2 goes to 0, which is sort of where we are really interested in, because this gamma 2 was the coefficient of the Jz square term. So now we have eliminated that from the picture by choosing this particular atom with these constants in it. To some approximation, it is 0. Therefore, we have got what we looked for earlier in that picture of the Q function. A nice case where you got a Hamiltonian that's effectively n times Jz, with no Jz square creating entanglement and doing all this funny business. There are other issues there, which is that, okay, if you add n, we are looking for the scaling with respect to n. If you increase the number of atoms with the same trapping potential, the wave function is going to spread out, and your factor eta, which is integral of the 4th power of the wave function, is going to change with that. So how do we get rid of that? Well, as a theorist, you can assume that you can have hard wall potential so that there is no spreading. But we make it nicer and say, okay, let's do a stronger than harmonic potential. So that it's not in a harmonic trap. Let's assume it's in some k r raised to q. Right? This is a sort of method to that madness. And you can compute the with respect to that q, how the scaling goes. And in the limit of q going to infinity, you will find that you will get this 1.5 factor there, which is the ideal case you are looking for. So we can start with n atoms in this state, do a superposition like this, then evolve it under the Hamiltonian or the Ghosh-Pitevsky equation for the Bose-Einstein condensate, and you can compute after the next pi/2 rotation, which are all those Hadamard's in the beginning and end that we talked about. You'll find that this is how the probabilities for the atoms to be in state 1 and 2 evolve. Okay. And you'll find that the evolution is such that it is controlled by this frequency, which has a factor of capital N in it, as well as the wave function spread, which is eta, and the parameter you're trying to estimate in this toy problem, which is gamma. So we seem to have achieved what we are looking for. We have got a relative phase that is going as n gamma 1 in this scenario, and and you get what you want. Because you have to think a little bit more. So I'll just stop with this. Well, the case is not ideal, and there are slightly different scattering lengths for the two states that we use, which leads to a position dependent phase, which means that these two curves, which are supposed to represent the wave function of the atoms, they don't pick up a relative phase smoothly, but rather, oh, sorry, run this again, you'll find that this is the ideal case. It will do it on its own. Yeah, doing it on its own. If you make this realistic assumption, you find that the relative phase actually changes as a function of position, because the two atoms don't atoms in the two internal states do not exactly behave the same way. So we can do more fancy pictures with it, but I don't want to bore you with that. You'll find that these atoms kind of separate out. The two modes of the BC tend to separate out in the same trap. So we have to address that, because we are looking for this relative phase in which one mode is picking up relative to each other, to the other. So these are all more details, but I don't want to bore you with that. Right? And in the end, you will get a certain signal. This is one point I also want to emphasize here, is that in the end, if you were to construct this experiment, what are you going to measure? You are going to measure the probabilities of the atoms in the BEC being in state 1 or state 2. That's in the end what you're going to measure. Right? And you can do it maybe as a function of time. You can measure what you are getting. So how do you extract the parameter that you're measuring out of it? This quantity gamma 2 in this case, gamma 1 in this case. It's a totally uninteresting parameter in some sense, but how do you get all the same? How do you get that out of this experiment? Because what are you getting? You're getting on this graph, right, some data point or a bunch of data. So the point I want to emphasize is that you need the theoretical development that goes with it to figure out what is the curve that I have to fit it to. Because all I know is that the set of points have some dependence on your parameter gamma. So you need the theory that goes behind with it in order to fit it to a curve, and then from that extract the value of gamma. If you have no idea what's happening, then these data points make no sense. And you cannot get the parameter that you're trying to estimate. So that's the only point I really want to stress in here. And these are cases with more atoms and what happens, and with different values of the potential that is holding the atoms. Well, for higher values, you see that you get better agreement between the theory and the experiment, so you are expected to do well in that scenario. But all these details have to go in. So That's essentially what I wanted to emphasize here, rather than impress upon you all the details of all this. And there are many questions here again, which one can think about. But more important are probably the questions that you may have. Okay. So that's all I wanted to say. I'm on time or slightly early, so we have some time for questions.
Hello, sir. So in the Ramsey, that diagram where you, the first Ramsey, typical Ramsey diagram, and then again you are dividing using beam splitter and then recombining that diagram.
Which
Again,
one? This
after
one?
that, so where you are getting n to the power 3/2 scaling.
Oh, that comes much later, right? That is when you have the nonlinear Hamiltonian,
Yes,
right?
yes.
Jump to it. This one?
No.
Here.
Maybe just state the question so that he can find the slide
So
corresponding.
what exactly happening in the second arm of the interferometer after that Ramsey?
Oh, you're talking about that interferometer picture.
Yeah, interferometer. Yeah.
This one?
Yes, sir. So in the second arm, what operation is exactly happening, and basically is it a amplification of the phase acquired in the first process?
No,
or-
this one.
Yes, sir.
This part actually nothing really is happening. It's just that once you have done this, you have to bring these beams back to interfere, right? Right. So earlier you would have put the beam split normal interferometer, you would have put the beam splitter here and then got the output out. So let's forget these two things. The JS square, let's assume that it's not there. Right? So what we are trying to say here is that this beam of light is going to put a phase on this beam of light. That depends on how many atoms that are coming in this way. And similarly, this beam of light is going to put a phase on the other one. That depends on the number of photons that are in this. And that whole thing is mediated by some kind of nonlinear interaction with some, say, cross-curve medium or something that's sitting there. So this is a very hand-wavy hypothetical thing.
Okay.
But the whole point is that whatever phase that is picked up is therefore dependent on the number of photons in the other arm, which is a huge advantage when you have 10 to the 20 photons with you. So the phase that you are trying to pick up is now amplified by that number. And then, of course, once you've done that, then you have to bring it back. So the remaining part is just to kind of bring it back.
Okay.
Other questions? Saikat, please.
Yeah, so this SU11 interferometers where there's this pair production where the phase is written and then brought back. Would that fall under the same category like non?
I have to.
So there also you have like the beam splitters are basically doing a pair production. There's a nonlinearity.
Then, yeah, it's also maybe Hall is the best person to answer because he wrote a paper on SU11. Oh, the question is SU11, does it fall under the nonlinear category?
So the question is about SU11?
Yeah.
Yeah, no, I think SU1 is basically a linear thing. You have asked the right person. I wrote a whole article about SU11 interferometry and how it's wrong to think about it as an interferometer. And so you could just look on the web and SU11 is basically a displacement detector of a linear sort, enhanced by the squeezing. And it's the same thing as making what were in the ancient days called back action evading measurements. So anyway, you could go look up that paper if you want to. Yeah. Oh, but I did have one other comment, Anil, which is this whole nonlinear scheme has been implemented optically using nonlinear optical effects by Mitchell's group.
Oh, okay.
It all works. So then there they would be determining, again, a thing that's probably useless to determine, but they'd be determining some nonlinear parameter for nonlinear optics.
Yeah.
Better than Heisenberg limit suggests you can do.
Oh, I didn't know that. So, well, there you have it. Somebody else was paying attention and actually made it work.
So any other question? So Anil, I have a question. Okay, please.
Sir, you were showing one slide on the BC and you said that we need that, we need that system because you have a Hamiltonian in the system, which you want to, you want to have a system that can generate that sort of Hamiltonian. So what part of the Hamiltonian are you exactly focusing
No,
on?
see,
The first slide regarding the
BC, right?
BC. Yeah.
so what I'm trying to say is that it has an
Yeah, this
effective
part,
interaction,
even
this part
I
here.
thought. So even a Kerr medium has this, right?
Yes, that was
nonlinear
the-
crystal.
That was a picture with the other one. That's what the case was also saying.
Okay.
That was
So-
actually implemented.
Yeah, okay. So that's what I was thinking. Even with the nonlinear.
So whenever you
Kerr
start talking about nonlinear and Hamiltonian in the same sentence, people get slightly sort of iffy about what you're talking about, because quantum mechanics, after all, is a linear theory. Therefore, you have to be specific as to what you're talking about as nonlinear.
No, I was saying that the last
This kind of
term in
term
the
does appear.
Hamiltonian. So that is the nonlinear interaction, right?
Yes.
That's why I was saying. So even a Kerr medium shows this.
Yes, that's precisely the point of that nonlinear interference.
Okay.
Very
So
good.
I was just asking whether you were looking for that part in the Hamiltonian, and that's why you went to a Bose-Einstein
Yes.
condensate, or? Okay.
Exactly.
Okay. Other questions? So Anil, I have this school of work and its cousins, batteries, and so on and so forth. And I also want to just bring in Dickey superradiance, kind of phase transition physics as well. One of the kind of prescriptions that people talk about is this Koch prescription, right? So to scale the Hamiltonian in such a way that if you do thermodynamic scaling, that everything scales linearly, because otherwise then you just drop the non-dominant terms and only deal with the dominant terms. So the Koch prescription, if you look at, let's say, the LMG model, the J square Hamiltonian that you've written, for the Koch prescription, what they do is they divide by n.
Yeah.
When to discuss the phase transition physics, right? So I have been likewise in the Dickey model, for instance, there is a square root n, right? And you can ask where does it come from, and it's essentially the volume of the cavity. Here as well, you had mentioned that there is this kind of soft trap to accommodate this fact. So the question that I have is a very general one, but we can situate it in the specific examples that are here, which is, often we do this in metrology, which is we will just say, I take a nonlinear term and I put it in and I just blah, 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 and Heisenberg scaling, right? But I think, or even beyond Heisenberg scaling, but I think that goes away if you take JZ square and divide by n.
Yes, of course.
And it also goes away if I don't allow you njz.
Yeah.
Right. And if you talk to people who do kind of that version of phase transition physics, they will say, why are you writing these Hamiltonians to begin with, right? And do you have a comment on this, or is there a discussion on this in the literature as to what to think about this, or how?
But see, I suppose in phase transition and these metrology, you're actually worried about two different things, right? So you are essentially worried about what kind of disturbance or what kind of change the phase transition brings about to every point essentially on your bulk system, right? You're not really interested in what the overall thing is doing. Right? Therefore, that's why you're always prompted to divide by this n, because you're sort of looking at what's happening at each location. But here, your entire system is your quantum. Therefore, there is nothing wrong in sort of ignoring that n or not writing that down, because this entire thing is going through. So the same question comes, can you use phase transition for metrology? If you start dividing by n, you find that, okay, it's not terribly great. But on the other hand, you know that around a phase transition, you are extremely sensitive to your parameter. Therefore, why not use it? And you will see it as a change in the entire system. If you go down and look at each atom sitting there and what's happening to it and how much change it's going through, you have to do all this division by n and all. So it seems to be, to me, two different problems. Right?
There I see it as not the n going either as Heisenberg, not exploiting the spectral norm of the Hamiltonian. That's but essentially the fact that the correlations being long range make your susceptibilities diverge, right?
Yeah.
So it's a different effect is the way I think about it. But
it is not a nonlinear effect. But the thing is that if you divide by n, then you will not even see that.
Yeah, the infinity is somewhere else.
You'll find that even in the phase transition, you will get 1 by root n. You cannot use it. But you just look at the whole thing, it works. Right? So it's because you're basically looking at two different questions. Is what I would answer that. So they are just, and it's a matter of physics, people are justified in considering that. That's fine.
There's one more question.
So, sir, if a process is slow, about that process, I want to measure something. And say if I prepare a cat state or so the problem comes that because of decoherence, the state dies out
Yes.
before before the process could complete. So are there any literature or people, have they used some sort of state which is immune to, say, dephasing?
Oh yes, that is a point that I guess briefly Carl mentioned. I don't think anybody has touched upon, which is the fact that how do these esoteric states stand up against decoherence, and in particular, in most cases, they're pretty terrible.
Mm-hmm.
Like from a noon state, for example, you lose one photon, you're kind of dead. Right? Nothing you can do with it. Actually, if you try persisting with the noon state and measuring, you do worse than short noise level. You're better off not using the noon state at all. So that question is, and there's one more part to comment about your question. Let's not even worry about time varying parameter, because that's also not really considered, because we are assuming your parameter is a constant. Therefore, or in other words, when you say a slowly varying parameter, this whole entire process has to complete before it actually changes significantly. So that also is really not considered in what we are worked out. So when you come to that scenario, a real scenario where you have to deal with all that, you have to work those details also in. How much time do I have to do the measurement? So instead of n, time also becomes a resource for you. You have limited time. You have to worry about doing it within that time. Therefore, you have to count it within in your n. And then decoherence is a whole entire different problem. And indeed, people are working on it. And there are interesting results about in interferometry if you have n photons at your disposal. So it's a fixed photon number state. How best do you arrange them? Do you put them in a noon state or some other state if you have losses? And you can show that noon state is particularly bad, but there are other optimal states that you can use. Then an even more interesting question is, okay, suppose your photon number is not fixed, then you run into a whole other set of problems in terms of what the Kramer bound gives sometimes will not make sense. So you have to worry about those aspects. So this is sort of what I wanted to give you a flavor of, where you go from the thoughts about what is the fundamental limits to how do you actually kind of get there in semi-realistic systems. And all these considerations therefore has to come into.
Other questions? Okay, otherwise, let's thank Anil once again. And I have the pleasure of presenting to Anil an elephant, something I've always wanted to do.
It's an elephant in a box. So.
An elephant in a box.
Thanks.